Hi, welcome to Proficiency Eagle Series Online. My name is Philip Liang, one of the tutor at Proficiency Education's Eagle class. In order to state rank and come first in the state, getting a raw mark of 100% is sometimes not enough. In this series of videos, I will be posting 4-unit challenge questions weekly, focusing more on how the examiners compare the answers if both students attain full marks. It's recommended that you try these questions yourselves and time yourself before going through the answers. So today we'll be doing a polynomial question. We're given a polynomial pz, which is that, and that k is between -1 and 1. We want to prove 1 on alpha is a root if alpha is a root. So because alpha is a root, we can just sub it in, and this would all equal to 0. And our goal would be to try and prove p 1 on alpha is also somehow equal to 0. So we can just combine all the fractions. And we realize that this is just p alpha, but negative. So that's negative p alpha. And p alpha is 0, therefore this is 0. So because p1 on alpha is 0, therefore 1 on alpha is a root. And that's how you do the first part.
1.
So moving on to the next part, we are given that pz has modulus of alpha does not equal to 1. And we want to prove that there is at least one alpha where the modulus is greater than 1. So we can use proof by contradiction where we assume that all of the roots of pz's are all roots, they are less than 1 because they're not equal to 1, and we want to prove they're greater than 1. So we want to prove by contradiction. But given the last part, because alpha is a root, 1 on alpha is also a root. So it comes logically that if you take the reciprocal, 1 on alpha must be greater than 1. And that already gives you a contradiction because 1 on alpha is a root. And therefore, your assumption is wrong, meaning that there exists at least one root alpha where it's greater than 1. Because all we assumed here is that every single root was less than 1, the modulus. So the contradiction, the opposite would be there exists at least one alpha greater than 1. Moving on to the next part, we want to prove this equation, and all these numbers look very familiar. So we want to just try and sub alpha in. So we know alpha is a root, so we can just do this. And is equal to 0. We can just try and factorize and see where we go from here. And I will want to move this part to the other side because it's the same thing. And we realize that everything is squared, so we can just square everything. And then finally, I can just take the modulus of both sides. And that's how you do those two parts. So moving on to this fourth part, we want to try and prove this inequality. It is probably the most tricky part of this question. And we want to use the third part because that's what we just found. And everything looks sort of similar, not exactly. And also, we want to use part 2, where alpha, the modulus of alpha is greater than 1. So even though there are modulus of alpha less than 1, we want to use the condition that they are greater than 1 in this particular question. And it will be important in the last part. So let's use the condition that alpha, modulus of alpha is greater than 1. So we can simply write, which is the left-hand side of part 3, we can simply write this is greater than alpha minus k all squared. So therefore, we can rewrite this equation as an inequality where it's just like this. Because we get rid of alpha, which is greater than 1. If we get rid of something that's bigger, it will become smaller. So when we get to this part, we realize they're all squares. So the modulus isn't really there. but in the final answer, there's a modulus around the alpha. So the way we can try and make the absolute values only around the alpha is if we let alpha equal to modulus of alpha cis theta. So I'm just writing it in its complex form, and I'll just simplify it. So I'm writing the real and complex components together. And then because these are both squared, we can just find the modulus of both sides. We can take Pythagoras. So these two parts cancel out, and we can simplify the rest by using sine squared plus cos squared theta equals to 1. So these two parts become alpha squared. So you're left with alpha squared plus k squared on the left hand side, and on the right hand side you have 1, and these two parts again cancelled out to become 1 plus k squared alpha squared. So once you get to this point, you can probably just try and factorize. So I'll just move some parts over, like so, and then one more time to get the final answer. And that's how we do that part. So moving on to the last part of this question, we want to try and use all the information that we were given, that we found, and we want to prove that all roots of pz have a modulus of 1. So this comes back to part 2, where we assume that pz, all the roots have a modulus does not equal to 1. It's greater than 1 or less than 1. So we think it's logical to think that there is a contradiction, because if the assumption is wrong, therefore the opposite is true, and therefore you've proved the question. So we can try and find a contradiction in part 4. So I'll just write it again up here. So this is from part 4. But we also know for this part, we assume that modulus of alpha is greater than 1. So if modulus of alpha is greater than 1, alpha squared is still greater than 1, and therefore alpha squared minus 1 is greater than 0. Additionally, going back all the way to the beginning, we know that the condition of k is that it's between -1 and 1 inclusive. So in other words, k squared is less than or equal to 1, or 1 minus k squared is greater than or equal to 0. And if we combine these two together, if we multiply them, we realize there is something wrong, because we get that this expression is greater than or equal to 0. But in part 4, we just proved that it was less than 0. So therefore, the only conclusion that we can come to is that there is a contradiction, and that your original assumption was wrong. And what was our assumption again? Our assumption was that, from part 2, in that pz has n plus 1 distinct roots. All of them have a modulus that do not equal to 1. And as a result, at least one root is greater than 1. And that's where the problem comes from. If there is a root where alpha, modulus of alpha is greater than 1, this creates this whole problem. So there can't be all roots alpha less than 1, because we already proved that in part 2. So there is only one solution left. And that solution is that, therefore, pz must have all roots modulus equal to 1, because there are no other options left. And one other thing I would like to talk about is, in this part, why did we not use modulus of alpha less than 1? So because there are roots alpha less than 1 modulus and alpha modulus greater than 1. That's because when we use modulus of alpha less than 1, we get the same solution, but in the end, we get this is greater than 0. We get this is greater than 0. And we can do this part again. And alpha squared minus 1, instead of being greater than 0, it will be smaller than 0. And this part is still the same. So we'll get, this will be smaller than or equal to 0, whereas from part 4, it will be greater than 0. So again, there is another contradiction. So we can simply say it's symmetry, whether we take alpha less than 1 or alpha greater than 1, because you come to the same conclusion both ways. It's just that this question, it wanted you to use alpha greater than 1 for this part, and not alpha less than 1. And that's it.